We discuss a lot about nuclear power, but what is nuclear power powered by? Uranium. Today we're going to discuss the process of fabricating nuclear fuel for the existing reactors that we have around the world. We are going to go through all the methods from extracting uranium ore from mining all the way to pellet manufacturing and it going inside the reactor. We're going to go through mining, conversion, enrichment, conversion again to uranium dioxide, and fuel assembly manufacturing. Without further ado, let's get into it. What we are discussing today is the so-called front end of the nuclear fuel cycle, which involves the fabrication of the nuclear fuel and it being used inside the reactor. And the video that we referred to last week was the back end of the nuclear fuel cycle, and this is how we handle the fuel after it's been used inside the reactor. So it can either be stored or it can be reprocessed, recycled and reused again. Starting off the front end process of nuclear fuel cycle, and we have mining. Mining is basically the process to extract uranium from underground or wherever uranium is found on Earth, and this is typically underground or underwater. Uranium is usually in the form of rocks underground, and it is pretty much as common as the element tin and around 500 times more common than gold. A naturally occurring uranium ore means the rock that contains some uranium inside can have a concentration from 0.3 all the way to 20% of uranium. 20% would be a very high concentration of uranium naturally found in a rock, and around 1% is the typical concentration that is found around the world. The most abundant uranium occurs naturally in Canada, Australia and Kazakhstan, and this is where most of the worldwide mining of uranium happens. There is mainly two ways to mine uranium, and this is first the conventional method of drilling the rock and extracting basically crushed rocks that contain a little bit of uranium inside and also other elements that are not of use, cleaning this rock or adding some sort of acid into it that dissolves the uranium and separates it from the rest of the elements, treating it in an appropriate way that doesn't make it dangerous or harmful for the environment, and using then the concentrated uranium that is extracted from that mining to go to the next process. However, another common technique that is used in uranium mining that has much less environmental impact, it's called in situ leaching. And how this process happens is that there's a few bores that are being drilled all the way to the uranium ore present underground, and the solution of oxygen or carbon dioxide is injected through these bores and reaches all the way to the solution that has the ability to separate the uranium from the remaining of the ore. Then once the uranium is separated, it is basically pumped out of the ore without really disturbing the environment or opening up this big open pit in order to mine the uranium rock itself. This method, as I said, has a much less environmental impact, and it has also the benefit that it doesn't expose the workers or the environment around to the underground radon that is present once you open up an open pit. After mining, the uranium ore or the leftover of the ore that is concentrated in uranium is being treated and purified and chemically converted into uranium oxide forms that can be a chemical form of U3O8 or UO3, and all of these forms vary in color and chemical composition. However, they are typically referred to as yellow cake, as you might have heard, because most of them have this distinct yellow color in their powder, and the concentration of uranium in yellow cake is around 80%. So it is quite high in concentration at this point, and it will be enriched further on. The next process is conversion, and this is basically done in order to have the uranium in a form that it can be used for enrichment. What that means is that naturally uranium occurs in a concentration of uranium-238 at 99.3%, and 0.7% only is the isotope uranium-235. However, the uranium-235 is the one that is mostly used in the nuclear industry, and therefore it is necessary to enrich the presence of this uranium-235 inside the natural uranium that we extract from underground. In order to enrich the uranium, it is easier to do that with a process that uses gaseous uranium form. Therefore, the yellow cake is transformed to uranium hexafluoride, which is a gaseous form under a little bit of a higher temperature than room temperature. So the conversion is a chemical process basically that changes the chemical composition of the uranium as a yellow cake to uranium hexafluoride, which at room temperature and in regular conditions, standard conditions, is a solid, but however at around 50 degrees Celsius it becomes a gas. This gas, the uranium hexafluoride, is now used to enrich the uranium. The enrichment happens mostly with a process called gas centrifuge, even though there are other processes as well, but this is the most common one and the one that I'm going to describe here. So how that happens is the uranium hexafluoride is injected in a big cylinder that spins around itself very quickly. And with the help of a centrifuge force, the heavier isotope of uranium, the uranium-238, is being pushed away towards the walls of the cylinder, whereas the lighter element, uranium-235, sort of remains around the center. In a sense, then we create kind of an area that has a little bit more of the uranium-235 than what the natural ore had, and therefore we can extract that middle part of the gas that has the higher concentration of uranium-235. If we extract this gas with a little bit of a higher concentration, then we can go through this centrifuge process again and again until we enrich the uranium-235 presence to a percentage that is useful for nuclear grade applications. And the percentage that is typically used in light water reactors around the world is 3 to 5% of uranium-235 over the uranium-238, which naturally is the most abundant one in the uranium fuel. After enrichment, the percentage of uranium-235 is the one that is useful for fabricating nuclear fuel. However, the uranium hexafluoride is still not in the form of uranium dioxide that is being used to create pellets. So there is another chemical process that goes into play here that basically transforms the UF6 chemical compound into uranium dioxide, UO2. After we have uranium dioxide in a form of powder, this looks like a grayish fine powder, we go through the process called pelletizing. Pelletizing, as the word suggests, is basically a process to make pellets out of uranium dioxide powder. So there is several processes that go into it, but a general description of it would be compaction of this powder into a so-called green body pellet, so a pellet that has the shape that we desire, which is approximately 1 centimeter in diameter, 1 centimeter in height. You can think of it as approximately the fingertip of your finger is approximately the size of a uranium dioxide pellet. So once these pellets are being pressed into their shape and desired size, they are being baked, or the word that we use in the nuclear industry is sintered, at higher temperatures and in atmospheres that are suitable for them to not interfere with any other elements that might be present, and they are being basically solidified and densified into their higher final density and taking up their shape, shrinking a little bit more once they are densifying and taking up their final shape that looks something like this, and then they are ready basically to be used inside the nuclear reactors. It is interesting to know that one of these uranium pellets holds as much energy as 800 kilograms of coal does, or over 500 liters of oil. And another fun fact is that 2 of these pellets can power a household for a full year. So basically you only need 2 of those in order to have electricity and power necessary for a house for a whole year. And there is several thousands of these present inside just one reactor core. After the pellets have been sintered, meaning baked, they are being inspected, their final shape is being treated in case they need a little bit of grinding, or in case that there are some faulty ones in the batch, such as cracked ones or ones that don't meet the inspection criteria, they are being basically pulverized and put back into the production line and reused again to make these pellets that basically qualify the standards and all the safety inspections for them to be used inside the reactor. So now the final step is basically to put these pellets into the fuel assemblies that we have seen in previous videos before, and they are being stacked the one on top of the other in thin rods that are usually made out of zirconium alloys, And these rods are then bundled all together to form the so-called fuel assemblies. A little bit over 100 of these fuel assemblies exist inside a typical light water reactor core and are being used to produce energy inside the nuclear reactor. So this was a basic introduction of the front end of the nuclear fuel cycle, from mining of uranium ore all the way to fabricating uranium dioxide fuel pellets that can be used inside the reactor. Let me know your thoughts about the nuclear fuel fabrication process in the comments down below. Let me know if you want me to expand in a particular process that I described in these methods. And also let me know what you think about the use of uranium dioxide as fuel, and if you would like to see potentially other fuels to be used in the nuclear industry in the near future. I work closely with nuclear fuel fabrication, however not uranium dioxide, but another type of fuel that I would love to describe in a future video and show you around the lab the process that we have developed to fabricate it. Let me know if that would be interesting for you, and I will make sure to make a video about that in the future. Don't forget to like and subscribe and turn on the bell notification icon. It's been Elina, your friendly nuclear physicist, and until next time, see you soon. And these rods are then bundled all together